when we talk about momentum, hopefully this is a term that seems familiar to us, right? We've at least heard the term momentum before, and we've said it in context, hopefully in the correct usage, but most of us have talked about momentum at some point in time. A big portion of this chapter deals with collisions. And what's a collision? Yeah, when two things hit each other. Okay? There's a couple different types of collisions we're going to talk about. But this chapter deals a lot with collisions. Okay? So two things colliding. We're going to look at how momentum can carry through that collision. Okay? What's it called when we don't create or destroy something? What's that called in scientific terms? It's not created or destroyed, but it is transferred, but it's not going away. It's not starting from scratch.
Transcendent.
No, it's not. No.
Okay. Well,
No. Starts with a C.
Change.
No. No. Conserved. Not created or destroyed is conserved. We weren't getting there? Okay. All right. So we're going to talk about two main types of collisions. The first of which is called an elastic collision. You're going to need to know the difference between these two types. First of which is an elastic collision, which is where things hit and then rebound off of each other. Okay, so what's another word for rebound? They bounce off. They bounce off. They don't stick together. They hit and they bounce off. So what would be an example of that type of collision that would happen in real life?
Basketball.
Yeah, basketball bouncing. What else? If you play pool, right? That's a really, really common example for an elastic collision. When you hit that cue ball, it transfers that energy to one of the others. Okay? In these types of collisions, we see a conservation of energy, a total conservation of energy. And we haven't talked about our energy chapter yet. We'll actually talk about that next. But you need to understand in a perfectly elastic collision, when things go exactly right, no friction, perfect world, we have a perfect conservation of energy. So that means all of the energy from one ball is transferred completely to the other ball. Okay, so they kind of just switch properties there. Okay, our other type of collision is called an inelastic collision. And this is where objects stick together. So they would collide and then stick together after their collision. You might be able to think of an example of this happening in real life. Hopefully you can. Anybody think of an example of this in real life?
throw those little sticky things and then stick to them.
Okay, yeah. Yeah, okay. All right.
The what?
Those little things like the hands, and you just go and it sticks to them.
Collide and then stick together and move on as one whole thing. What would be an example of that?
What about those
Train.
darts?
Oh, a magnet? Like
Like the two magnets that you like very smooth.
Yeah.
You throw them in the air and they're like.
okay. Yeah. Think a train, okay, yeah. Would it like couples with another train? Moves on? Good. I'm thinking like if two cars are wrecked, right? And it becomes one pile of car and they move, right? A little gruesome, but okay. Or if you would tackle somebody, right? Two people might be moving from a different direction. You tackle them and fall down. That would be an example of an inelastic collision as well. Okay, are we envisioning what's happening there? Okay. All right. So now I'm going to give you the equation for momentum as a whole. Momentum. Momentum is identified by a lowercase p. Lowercase p. And what does the delta tell us here? What's the triangle here tell us? Delta.
Change in.
Not final, but change in. Right? It means final minus initial. Okay, final minus initial. Okay, so if we're looking at momentum at one point in time, do we need to use the final minus initial? We're just looking at one point in time? No. Okay, so the only thing we would change there is we just say P equals M times V. That's it. That's the only thing that would change. Okay? The delta tells us that we can do final minus initial. Okay, momentum is a vector. So what does that mean? It has to have what two things? Very good. Magnitude and direction. Okay, magnitude is the size or the number. Direction can be a positive and a negative here. It can be a north, east, south, west. We can use any of those things, but it is really important that we do include that direction. Okay. Since momentum is a vector and velocity is a vector, that means momentum and velocity have to be in the same direction. Right? That should seem very self-explanatory for us. If I am moving in the north direction, right, my mass is moving in the north direction because that's my velocity, so that means my momentum should be in the north direction. Okay, so you have to pay attention to if your velocity is moving south or west, what do we need to include there with that number? Moving south or west, what has to be included? A negative. Okay? So make sure that your momentum ends up being in the same direction as your velocity. Units for momentum are kilograms times meter per second. Okay, do we see where those are coming from? Kilograms times meters per second. Okay? Kilograms times meters per second. So mass has to be measured in kilograms. Velocity has to be measured in meters per second. Okay? Do we remember the shortcut from kilometers per hour to meters per second?
Is that the times point?
Somewhere. That's right. Times 0.2778. This goes from kilometers per hour to meters per second. If you want to write that down again, we might use that a couple times this chapter. So just... You don't have to use a shortcut. A T-chart will always work, but this will save you a little bit of time. Sorry, do we have what we need there or not quite? Okay, think about this. A large truck and a small car are moving at the same speed. Okay, exactly the same speed, right, parallel to each other. Which is more difficult to slow down, the car or the truck? The truck. Why is that the case? Its mass is larger. So these two are traveling at the same velocity. Which would have the greater momentum? The truck. It has greater mass. Okay, so that means it's going to be more difficult to slow down. Things with greater momentum take a greater force to change their momentum or to change their direction or whatever. Okay, so hopefully that's pretty common sense to us. The bigger object is going to take a longer time or more force to slow down. Okay, that's if they're traveling at the same velocity. It's possible that they could be traveling with equal momentum, right? In which case, what would the little car have to be doing? Going faster. Good. The little car would have to be going faster if they want to be traveling with equal momentum. All right, very good. All right, let's try this one here. A runner is traveling at a velocity of 3.21 meters per second west. If the runner has a mass of 65 kilograms, what is the momentum of the runner? Okay, this one is really as easy as it seems. Okay, in this case, it doesn't ask for the change in momentum, right? We're just looking for the momentum at that point in time. So we don't need the delta, the change in. Okay, you can always put it in there. That really makes no difference, especially here, because we're assuming that his starting was, at 0 or whatever. His initial velocity was 0. So we're solving for momentum. Our mass is 65 kilograms. Our velocity is 3.21. Okay, and our momentum came out to be about 208.65, and our units for momentum are good kilogram meters per second. Okay, questions? Okay. You're right. You're very right. Thank you. Very good. Negative. You are correct. Thank you. So this really should be negative there as well. I missed that. Thank you. Okay. Do we know why that's going negative? Okay, because it's west. I wasn't paying attention. All right, very good. A rolling boulder is found to have a momentum of 4,015 kilogram meters per second east. If the velocity of the boulder is 16.4 meters per second, what is the mass? So we were given a momentum of 4,015. We don't know our mass. We know this is 16.4. We're going to divide that over. And what did we get? Yeah, Trev, what'd you have?
2,448.47.
2,448. I had one decimal place off of that. I had 244.8. Okay. So we looked at basic momentum object moving in one direction without anything stopping it. Now we're going to look at the force that it would take to change an object's momentum. Okay? Okay, we're going to look at adjusting Newton's second law here. Okay, so you don't have to write down every step of this equation derivation here, but I want to walk you through it. Okay, Newton's law said the sum of forces, right, or the net force is equal to mass times acceleration. Okay? And so all we did here is we took the net force equals mass times delta V over delta T, right? What is this equal to right here, delta V over delta T? It's equal to acceleration. All we did is a little substitution here, okay? So that gives us force, if I write it out a little bit clearer, M times delta V over T. Right? All we did was rearrange Newton's second law there. M times delta V over delta T. Okay? What does this look like right here?
Momentum.
Yeah, that looks like momentum, right? The change in momentum. So we're going to be able to now identify force with momentum. Okay? And so this final equation here gives us net force. You don't have to write this Greek letter there. That just means net. Okay, or force equals change in momentum over change in time. Okay, so all we did there was take Newton's second law and substitute it down until we got what we needed. Okay, all of these things are interchangeable and related. So we're able to bring this to this equation. Okay, you can rearrange this also if you wanted to solve for momentum. Delta P would equal force times delta T. Right? These two equations are exactly the same. They're just rearranged. Okay, so you can think about it either way, but one of these equations needs to go on your equation sheet. Okay, one or both of them. It makes no difference. All right, let's try one here. What force is required to stop a 488 kilogram wagon moving at a velocity of 52 meters per second north in a time of 2.3 seconds? Okay, so our wagon is moving north. It weighs 488. We want to bring it to a stop in a time of 2.3 seconds. So how much force do we need to apply to bring it to a stop? That's what this question is asking. Were we given momentum in our problem? No. What were we given? Mass and velocity, right? So we can solve for momentum first outside of this equation and then plug it in. Or you can just say mass times velocity over delta t. Okay, do we see that little substitution I made right there? Okay, is everyone okay with that? You can always solve for delta p out here and then just plug it in if you'd like to. Okay, that makes no difference the way that you want to do that. All right, so I'm going to say that force is equal to mass, which is 488, times change in velocity. What's our final velocity here? 0. Good, that's really important. A lot of you will just want to take 488 times 52. Okay, and it's really times negative 52 because we're subtracting final minus initial over time, right? If my object's moving in the positive direction and I'm applying a force to slow it down, my force has to be in the negative direction. It has to be opposing that motion in order to slow it down. So we need to be thinking in terms of that. Okay, so 488 divided by negative 52. No. 488 times negative 52 divided by 2.3. Okay, did we get about negative 11,033 newtons? Okay, yeah.
So if it was moving, it's like this 0 minus 52 because they changed
Mm-hmm.
velocity. Okay, sorry. So if it was negative,
Mm-hmm.
whereas then we positive.
So if it was moving south instead of north, right, it would look like this. We would go 0 minus negative 52, right, and it would turn into a positive. That's right. Okay, because if it was moving south, we want our force to be stopping it, which would be moving north. Good question. All right. Force should always be in newtons. Okay, so anytime we solve for a force, we're going with newtons there as our. And the negative here tells us it's moving south. If you leave that negative off, you need to write out south. Okay, so I know you know what direction it's going. Okay? All right. What's this 55 newtons tell us? The weight. That's right. So to get that object's mass, we need to divide that by 9.8. Okay, that one is a little tricky. This is not the force right here that's making it come to a stop. This is its mass. So Fg equals 55. So mass times 9.8 equals 55. Okay? That's where you have to start there. Okay, what do we get for our time here? Point what? 4.81. Okay.
But
4.8. Okay, questions there? All right. That is it for notes today.